Hi, and welcome back to the Physics 102 challenge videos for McGill Physics 102 Introduction to Electromagnetism. As always, I'm Matthew Heffernan, and I'm here to work out a challenge problem for this week. So this week we're actually not going to be doing a challenge problem, we're going to be doing an intermediate problem we didn't have time to get to in class, but it's particularly important going forward, because this is the exact kind of question you can anticipate to see on a final exam. So what we have here are two current-carrying wires. So the question reads, you find a current-carrying wire with unknown current I. Have that here. To determine how much current goes through this wire, you place a wire parallel to it, 5 centimeters away, and run a current I1 is 5 amps through it. Your wire feels a force of 2 newtons toward the wire with unknown current. What is the magnitude and direction of the unknown current? So we have here specified is we have just I, which is unknown, and a length of wire. And we know the direction of current I1 because we chose it. This is how we're testing it after all. We have the force of 2 newtons, and we have the separation here. So we have what we need to set this up. We can take a few steps back and figure out what's going on with this. So the first thing we can do is we can find the direction of the magnetic field here at this point on the wire. So if you remember right-hand rule number 2, that's this one. So as I mentioned in class this past week, your index finger will point in the direction of the current, your middle finger will point in the direction of the magnetic field, and your thumb will point in the direction of the force. So what we have here is we know the direction of the current is up this way, and the direction of the force is this way, so we know that here the direction of force is coming out of the page. So let's draw that like that. Okay, so what we can do here is now we can sort of break this down to find the magnitude of the magnetic force. So what you remember is that the magnetic force is given by the formula F equals I L B sine theta. Now the other thing we know is that the length of this wire here, which I haven't specified actually, is 1 meter. So here, let me write L equals 1 meter. Okay, so now we can rearrange this algebraically, and we can say that, oh, and we call this I1 because it's the force on the wire carrying I1. So let's go ahead and rearrange this algebraically. So we know that if we rearrange this, B is equal to F over I1L sine theta. Well, we know already by the right-hand rule that theta is going to be 90 degrees, so sine theta is going to equal 1. So we can just erase that because it's just equal to 1. We can substitute the values in here, and what we find is that the magnetic field, magnitude of the magnetic field, is equal to 0.4 Tesla. Okay, so let me put B here to label the direction there at the wire, and let's write down that we know now that B is equal to 0.4 Tesla. Great. So the next step is to think about the current in the other wire. So the first thing we can do is, as was mentioned by me in the lecture this past week, and as well in the summary slides, when two parallel wires have current going in the same direction, they'll feel an attractive force between them. We didn't even have to know the direction of the magnetic field to know that, but this would imply directly that I is in the same direction as I1. But let's be a little bit more rigorous about that, because the more rigorous we can be, the more sure we are of our answer. So what we can do is we have this coming out of the page. So we know that it's curling this way from I. So we know that B is also going to be out of the page here, out of the page here, and it's going to be into the page here and into the page there. Out of the page here. Okay, so now what that tells us is that by right-hand rule number 1, magnetic field is the direction our fingers curl. Thumb is automatically in the direction of the current. So we see if we put our fingers in this orientation, the current has to be upward, and then we'll get coming out of the page there and going back into the page on this side here. Okay, so let's just draw that in. Great. Now we know that current I is going upward, and we know it by 2 different ways. First, by remembering that 2 current-carrying wires, 2 parallel current-carrying wires, with currents going in the same direction attract. That alone tells us that I has to be going up. And we know by the right-hand rule that this makes sense. Okay. Now what we want to do is we want to find the magnitude of that current. Well, we know the formula for the magnetic field. So you know that B is equal to mu naught I over 2 pi r. Okay, but r here is just going to be 5 cm. So let's write that over here. R equals 5 cm. We know that B is 0.4 Tesla. Mu naught is given to us. 2 pi is just a constant as well. So let's go ahead and rearrange for the current. So we know that I is equal to 2 pi RB over mu naught. If we substitute in values, we know that mu naught is equal to 4 pi times 10 to the minus 7 Tesla per meter. Tesla meters per amp. Sorry, I got the units wrong on that one. Tesla meters per amp. Now we can substitute all of that into our formula here. So we have 2 pi times 0.05 meters times 0.4 Tesla divided by 4 pi times 10 to the minus 7 Tesla meters per amp. And that will give us a value for the current I equal to 1 times 10 to the 5 amps. So now what we know is by putting this current here with I1 equal to 5 amps, we found, using the force exerted on it, the right-hand rule. We've actually used both right-hand rules. And then the formula for the magnetic field. We now know that the magnitude of this current I is 1 times 10 to the 5 amps, and we know its direction has to be facing up.